Welcome to the first part of video lecture series for the electrochemical methods of analysis. Basically, the first part will comprise of 4 sections in which we'll be discussing the basic overview of electrochemical methods, the classification of electrochemical methods in which cell potential is under the standard conditions, as well as when cell potential is under the non-standard conditions, and we will also have a general overview of various electrochemical methods and their appropriate application. All electrochemical cells are based on redox reactions, which are made up of 2 half reactions. So before we delve into the lesson proper, we must first have to learn how to balance redox reactions using the half reaction method. So we have here an unbalanced redox reaction specified under an acidic medium. For the first step in balancing this, we need to divide the reaction into 2 half reactions. So we have separated the reaction of permanganate and the oxalate. Second is we need to balance the atoms other than hydrogen and oxygen. We could see here that the manganese is already balanced, so we don't need to insert any stoichiometric coefficients. On the other hand, the carbon here is still unbalanced, so we will put 2 here to make it balanced. Now we have both 2 carbons on the reactant and product side of the reaction. Next, we will balance the oxygen by adding water. Since there are 4 oxygen here, we will be adding 4 water on the product side to make it balanced. While here, we could see that this is already balanced since we have 4 oxygen on the reactant and product side. After adding the water, we're going to balance the hydrogens by adding hydronium ions. Since there are 2 times 4, 8 hydrogens on the product side, we will be adding 8 hydronium ions on the reactant side. Next is we need to balance the charges by adding electrons. Since there are a total of positive charge of 8 for the hydronium ions, while we have a total of negative charge of 1 for permanganate, then 8 minus 1, we have a total of positive 7 charge for the reactant side, while we have a total of positive 2 charge for the product side. We could observe that the transition from positive 7 to positive 2 of charge indicates that we have gained 5 electrons. And so we will be adding 5 electrons on the reactant side. While here, we have a total of negative 2 charge on the reactant side, and we have no charge on the product side. The transition from a negative charge to 0 charge indicates that we have lost 2 electrons. And so we add 2 electrons on the product side. Then we need to make the number of electrons equal for both of reactions. And so we multiply the whole equation here by 2, while we multiply the whole equation here by 5. And thus, both of the reactions will have 10 electrons. So this is the balance equation for the first half reaction. And this is the balance equation for the second half of reaction. And for the final step, we need to merge the 2 balanced half reactions. And since there are equal number of electrons in the product and reactant side, we could already emit this. And thus, we have our final balanced redox reaction. Now, how do we define which of the reactants is the oxidizing or reducing agent? Since we could see here that the manganate had gained electrons during the half reaction, thus it is the oxidizing agent. While we could see here that the oxalate had lost 10 electrons during the half reaction, thus this is the reducing agent. Now we have here an unbalanced redox reaction specified under a basic aqueous solution. So we will just repeat the first step in which we need to divide the reaction into 2 half reactions. We will also repeat what we have done in the second step, but for this case, we could see here that the carbon and the nitrogen are already balanced, and also for the case of manganese here. So we don't need to put any stoichiometric coefficient. We will also repeat what we have done on steps 3 and 4, where we will balance the oxygen by adding water and balance the hydrogen by adding hydronium ions. Now, this distinct additional step is what makes it different from the last time we made on acidic medium. Since this is a basic medium, to neutralize every hydronium ion that we added, we will be adding hydroxide ions on the both sides of equation. Since there are 2 hydronium ions here, we will also be adding 2 hydroxide ions on the both sides of equation. Same for this, since we have 4 hydronium ions here, we will be adding 4 hydroxide ions on both sides of equation. And as I said, the hydroxide ion will neutralize the hydronium ion, which will yield water. And thus, this becomes water. Now, we will just repeat the process of balancing the charges by adding electrons. You may pause the video and try to analyze on your own on how we arrive at this number and placement of electrons. Then, we need to make the number of electrons equal for both half reactions. After multiplying, this is a balance equations for both of the half reactions. Now we will merge the 2 balanced half reactions, and thus this is our final balanced redox reaction. Since the half reaction of cyanide showed that it had lost electrons, it would be our reducing agent. And since the half reaction of the manganese showed that it had gained electrons, it will be our oxidizing agent. So let's get started with the basic overview of electrochemical methods. Electrochemistry is the study of relationships between the electricity and chemical reactions. It also includes the study of both spontaneous and non-spontaneous processes. Electrochemistry is also the study of electron movement in an oxidation and reduction reaction at a polarized electrode surface. So what is the significance of electrochemistry in analytical techniques? So various analytical techniques actually uses measurement of potential, current, or charge to determine an analyte's concentration or to characterize an analyte's chemical reactivity. We have two types of electrochemical cell, the electrolytic and the galvanic cell. The distinction between these two is that the electrolytic cell have an electric source which can control or change the flow of electrons, therefore making the overall process non-spontaneous. While the galvanic cell will only have a voltmeter, which its sole purpose is to record the overall cell potential of the electrochemical cell setup. It doesn't affect or control on how electrons will flow, and therefore making the overall process spontaneous. But for this, we will mostly focus on galvanic cell. To make a galvanic cell setup, we basically need two types of electrodes. First is the anode, which will be our source of electrons. Oxidation occurs in the anode since it is the one who is responsible to lose or to provide its electrons, while the cathode will be the receiver of electrons. Due to the gain of electrons, thus the reduction occurs in the cathode. We will also need an external circuit, which would help the electrons to flow from anode to cathode, as well as the voltmeter to record the cell potential. We will also be needing the electrolyte solutions that will facilitate the conversion of metal ions. And lastly, we need the salt bridge that will connect the two sides of electrochemical cell. The salt bridge provides electrolytes needed to neutralize the solutions in both sides of the cell. This is a simulation of what happens in a galvanic cell on a molecular level. We have a solution here of zinc sulfate and copper sulfate. The simulation shows how electrons are flowing from the zinc anode to the copper cathode. It also shows that each time that the zinc provides an electron, it loses a zinc ion that accounts for its depletion. While every time the copper receives an electron, it takes copper ion from the copper sulfate solution. We could also see that as the positive charge and negative charge builds up in the solution, the salt bridge will provide its needed ions to make the reaction spontaneous until the anode is depleted. So now we will be practicing on how to write electrochemical cell notations. I just included the electrolytic cell here in order for us to clearly understand how to write the anode and cathode part of the cell notations. So we have our galvanic cell here. We could see that the electrons are flowing from the cadmium metal. Therefore, it is our anode. When we write cell notations, we always start from the anode half cell. First, we will write the solid metal used as anode. So we put the cadmium here. And the single vertical bar indicates a phase change within the half cell. After the vertical bar, we write the ions participating in the aqueous solution with its concentration if it's indicated. For this case, we have 1 molar contained in the anode half cell. And then we write 2 vertical bars here, which represents the salt bridge. And then we will proceed to write the contents of the other half cell where the cathode is placed. In this case, we write the ions participating in the aqueous solution first, and we write the single bar to represent a phase change for us to proceed of writing the cathode metal used. For this case, the copper gains the electrons, therefore it is our cathode. Unlike the galvanic cell, in electrolytic cell, with the help of a power supply, we were able to reverse the flow of electrons, making the copper as the anode here, as opposed to what we have seen from the galvanic cell. Since we are always starting to write the notation from the anode half cell, we will proceed to write the contents of the anode half cell, starting from the solid copper metal anode, then to the metal ion participating in the aqueous solution. And then we will proceed in separating the half cell notations using the double vertical bar and proceed to writing the contents of the cathode half cell. Here we could see the difference on how we write these cell notations. So it is important to write the cell notations properly, especially if chemists are planning to make an electrochemical setup in the laboratory. With properly written cell notation, we are able to identify how electrons should flow. Now we will be practicing how to write the redox reaction from cell notation. First, we will write the reaction of our anode, which is the copper. The anode is the one who is depleting, so we could see here that the anode produces copper ions in the solution. The copper ions have a charge of positive 2, which means the anode loses 2 electrons every time it oxidizes. Next, we write the reaction for our cathode, which is the silver metal. The anode is the one who becomes thicker during the process. So we could see here that the cathode takes silver ions from the aqueous solution to suffice for each electron it receives. But we need to balance the electrons here. Since the silver metal receives 2 electrons every time the copper metal oxidizes, we will have 2 silver ions taken from the aqueous solution of the cathode half cell. every time that the silver metal undergoes reduction process. And this is our final balanced redox reaction for this cell notation. With every concept that we have learned so far, try to write the electrochemical cell notation for this reaction. You may pause this video and you may write your answer in the comment section. Voltmeter measures the overall cell potential for two half reactions combined. But what if we just want to measure the potential of a half cell? For example, what if we just want to measure the cell potential of this copper metal? And this is where the standard hydrogen electrode is introduced. SHE consists of a platinum wire that is connected to a platinum surface in contact with an aqueous solution containing 1 molar of H plus in equilibrium with H2 gas at a pressure of 1 atmosphere. Let's take a look and see what happens at the standard hydrogen electrode. In the hydrogen electrode, hydrogen gas is bubbled around the platinum electrode. In the molecular view, the platinum surface catalyzes the oxidation of hydrogen molecules to protons or the reduction of protons to hydrogen gas. At the electrode, the hydrogen gas can be either oxidized to form hydrogen ions or the hydrogen ions can be reduced to form hydrogen gas. Hence, two reactions are possible on the electrode. Oxidation H2 gives 2H and 2 electrons. Reduction 2H and 2 electrons gives H2. This reaction gives the standard electrode potential equivalent to 0 volts, which can be served as a reference that can act as both anode and cathode. So here is an example where SHE acts as an anode for computing the cell potential for the copper metal cathode. And here we could see that the SHE acts as a cathode for measuring the potential of the zinc metal anode.
So cell potential, also known as the cell voltage or the electromotive force, is the electric potential difference between the anode and the cathode. Particularly under this section, we will be focusing on the standard conditions, which operates under 25 degrees Celsius and a pressure of 1 atmosphere. Then from this, we also know that the reactants and the products also have a concentration of 1 molar. So here's the list of reduction half reaction, where it's arranged from the reactions with the highest potential down to the lowest. The greater the potential, the greater for the substance to be reduced. And the opposite outcomes apply to those with the lowest value since they are easily oxidized. For example, we have here Ag positive, which has a greater reduction potential than iron 3 plus. So Ag positive is able to oxidize iron 3 positive since it has a higher reduction value. These reactions are also reversible, and what happens is that the reaction shifts from reduction to oxidation. And this is just noted by a change in the sign. So we just have to change their signs if we were to get the oxidation part. Lastly, the stoichiometric coefficients of the reaction species have no effect on the value of the cell potential. So here are some of the units that we have to remember, where 1 volt is also equal to 1 joules per coulomb. Then F stands for Faraday's constants. We also have the universal constant R, which is equals to 8.3.14, rather correct. It is 8.314 joules per mole per K. So let us now apply the lessons by solving this problem that we have here. So we are asked to calculate the cell potential and predict if the following reactions are spontaneous under standard conditions. So for part A, all we have to do is determine which of these species undergo reduction and oxidation. So by doing that, we have now determined the species undergoing reduction and oxidation. So always remember oil rig, where oxidation is the loss of electrons and the reduction is the gain of electrons. So the reduction potential that we have is 0.0 volts. Then the potential that we have for the oxidation process is positive 0.34. Now we just have to change this or input these values into our given equation, which will now give us the result of negative 0.34 volts, which is considered non-spontaneous since it has a negative charge for the electric potential. Though if we were to change these reactions where these where the products are now the reactants and the reactants are now the products, then we will be having a spontaneous reaction, since as we have noted from our previous discussion that we just have to change the sign. But however, for this reaction, this is considered non-spontaneous. So let's now go to part B. So we just have to do the same, where we have to identify which species undergo reduction and oxidations. And we also have these values na. These values can also be found on the table that we have provided a while ago. So we just have to supply these values into our given equation, and what we have now is a positive 0.082 volts, which is considered spontaneous since the electric potential is positive. So for this part, we will be focusing on the free energy and how it is related to electric potential. So G, which is known as gives free energy, measures the spontaneity of the process at a constant temperature and pressure. It is also related to the electric potential given by this equation, where gives free energy can be determined by multiplying the total number of electrons involved in the process times the Faraday's constant and the electric potential. At the same time, G is also related to the equilibrium constant K, where the Gibbs free energy is determined by multiplying the universal constant R to the given temperature and by multiplying it to the natural log of the equilibrium constant K. So this is the given equation if we want to determine the electric potential. Or we can also rearrange this equation depending on the conditions that we are given. So to summarize those, this diagram represents the relationship between the Gibbs free energy, the electric potential, and the equilibrium constant. So you just have to use the following formulas given in order to convert one form to the other. So we also have this table here where reactions are either considered spontaneous, or in equilibrium, or it can also be considered non-spontaneous depending on the values that we have obtained. So for this one, we have a new problem where we are asked to calculate the standard free energy change and the equilibrium constant K at 298 Kelvin for the reaction given here. So just like what we did on the first two problems that we have, we just have to identify which part undergoes reduction and which part undergoes oxidation. So now that we have that, we just have to measure the electric potential. So the electric potential that we have for this one is positive 0.43 volts, which is considered spontaneous. Then to measure the Gibbs free energy, all we have to do is use this equation where we just have to supply the total number of electrons. So we can see that that both reactions have 4 electrons each. So we just have to input 4, then this one is Faraday's constant, then this is the electric potential. We just have to multiply these values and we will be getting negative 1.7 times 10 raised to 5 joules per mole. However, we must know that the Gibbs free energy standard units are in kilojoules. So we just have to change joules into kilojoules by dividing it to 1,000, since 1 kilojoule is equal to 1,000 joules. So we will now be getting a value of negative 170 kilojoules per mole for our delta G. And by using our reference from the table that we have provided here, a negative value. So G has a negative value. We have a positive value which is greater than 1. Then for delta G, we have a negative value that is less than 0. So we just now have to determine K in order to predict if the reaction is really indeed spontaneous. So after that, we just have to solve for K. So a while ago, we also mentioned that K is also related to delta G. So we just have to use this formula in order to calculate for K. So we just have to modify the equation to have K on this side and all the other parameters on the other side of the equation. So we just have to plug in the values that we have. So this is our calculated value for the Gibbs free energy, and we just have to supply the universal constant R with the temperature, and we will be getting the value of 69. However, we have to note that this is still in the natural logarithm of K. So we just have to use E, and we just have to solve E raised to 69, which will give us the value of K, which is now 9.25 times 10 raised to 29. We also have to note that K is a unitless parameter, so there's no need to include any sort of unit for this one. So from what we mentioned before, G is negative, then the electric potential is positive, then for K, then K is greater than 1, then we can conclude that this reaction is indeed spontaneous.
Good day, everyone. I'm John Lucero. And from Julian's discussion, we have already learned how to calculate the EMF of a cell when the reactants and products are under standard conditions. Now, however, as a voltaic cell is discharged, the reactants are consumed and the products are generated, and so the concentrations change. The EMF progressively drops until the E is equal to 0, at which point we say the cell is dead. In this lesson, we're going to examine how the EMF generated under non-standard conditions can be calculated by using an equation first derived by Walther-Nernst. Also, we'll have a brief discussion about the components of common batteries and fuel cells as applications. Let's start by understanding EMF calculation. Again, EMF, or electromotive force, is essentially the driving force behind electrochemical reactions. When the conditions deviate from standard, such as changes in concentration or the temperature, we turn to the Nernst equation to accurately calculate the EMF. Now recall that in this equation, the free energy change for any chemical reaction, or the delta G, is related to the standard free energy change for the reaction, or the delta G naught, where the quantity Q is the reaction quotient, which also has the form of equilibrium constant expression, except that the concentrations are those that exist in the reaction mixture at a given moment. As also mentioned earlier, that delta G is equal to negative NFE, and so by combining these notions, it gives us this equation, which is our Nernst equation. Now, this equation essentially provides a framework for determining the standard EMF under non-standard conditions. And so by incorporating variables like the temperature and the reaction quotient, we can precisely calculate the EMF of a cell reaction regardless of the conditions. Interestingly, when T is equal to 298 Kelvin, the quantity RT over F becomes equal to 0.0592 with units of volts. And so the Nernst equation can also be simplified to E is equal to E naught minus 0.0592 volts over N log Q. Now let's consider this example where we have a cell reaction and want to calculate its EMF under non-standard conditions. In problems like this, we use the Nernst equation to adjust for changes in the concentration or temperature and find the accurate EMF of the cell. Now, just to give you some key points, in general, increasing the concentration of the reactants, which directly relates to decreasing the concentration of the products, increases the driving force for the reaction, resulting in higher EMF. Now, conversely, if you decrease the concentration of the reactants or increase the concentration of the products, it causes the EMF to decrease from its value under standard conditions. And going back to the example, the first step is we get the expression for the reaction quotient, which is generally the molar concentrations of the products raised to their stoichiometric coefficients over the molar concentrations of the reactants raised to their coefficients as well. And from this, we get a reaction quotient of 5.0 times 10 raised to negative 11. And next, we plug in the values, or we use direct substitution into the Nernst equation. Here, the standard EMF is 0.79 volts, and 6 electrons are transferred from the reducing agent to oxidizing agent, and so the N is equal to 6. Now, plugging in the values, or using direct substitution, we get E is equal to 0.89 volts. Now, moving on, in the voltaic cells we have looked thus far, the reactive species at the anode has been different from the reactive species at the cathode. Now, however, cell EMF can also depend on the concentration, and so a voltaic cell can be constructed using the same species in both half cells as long as the concentrations are different. A cell based solely on the EMF generated because of difference in concentration is called the concentration cell. Let's delve into a specific example of a concentration cell involving nickel. We can see that the oxidation of nickel occurs in the half cell containing the more dilute solution or the anode, while the reduction occurs in the half cell containing the more concentrated solution or the cathode. Now, the EMF of this concentration cell can be calculated also using the Nernst equation. In this equation, the E represents the cell potential, the E naught is the standard cell potential, and Q is the reaction quotient. And by applying the Nernst equation to this nickel concentration cell, we find an EMF of positive 0.0888 volts at 298 Kelvin. And this demonstrates the impact of concentration gradients on our cell potential. We now move on to the discussion of the components of common batteries and fuel cells. Now, these devices are crucial for storing and harnessing electrical energy, and understanding the components and mechanisms of these energy storage systems is vital for understanding their functions. The first one, a battery is a portable self-contained electrochemical power source which consists of one or more voltaic cell. Batteries consist of an anode, a cathode, and an electrolyte. Common types of batteries include alkaline batteries, lead-acid batteries, and lithium-ion batteries, each with unique electrode materials and electrolytes. Now, for the fuel cells, the thermal energy released by burning fuels can be converted to electrical energy. Voltaic cells that undergo this conversion utilizing traditional fuels like hydrogen and methane are termed as fuel cells. It is important to note that fuel cells differ from batteries as they are not self-contained units. Rather, a constant supply of fuel is required to sustain the electricity generation process. And that would be all for the cell potential under non-standard conditions.
Now let us proceed to the last section of this lesson, which is the general overview of various electrochemical methods and their appropriate application with a focus on analyte specification. Electrochemical methods offer a diverse toolkit for analyzing and understanding the chemical systems. These techniques rely on the interplay between electrical and chemical phenomena at the interface between an electrode and a solution. This discussion will delve into various types of electrochemical methods, exploring their mechanisms, ideal analytes. First, let us discuss the classifications of electrochemical methods or its techniques. For this specific section, the electrochemical methods can be classified into two, which are bulk and interfacial techniques. So bulk techniques are those methods that measure the properties of the entire solution, such as conductivity, which reflects the total ionic concentration. An example is conductometry, where changes in conductivity upon the addition of an analyte are used for qualitative analysis. The other one is interfacial techniques, wherein these are the methods that focus on the electrode-solution interface, where electron transfer reactions occur. They are generally more sensitive and can provide more information on specific analytes. Common examples include potentiometry, coulometry, and voltammetry. Now, let us dig deeper into the interfacial techniques. Let us explore three prominent interfacial techniques in detail. So for the first one, we have potentiometry. So potentiometry measures the potential difference or voltage between two electrodes, typically a reference electrode and a working electrode. The potential difference arises from the tendency of the analyte to undergo oxidation or reduction at the working electrode, thus establishing an equilibrium potential. It is applicable and ideal for ions that are readily participating in redox reactions, like for metal ions, examples are sodium and potassium. Then we have our pH, which is through a use of a glass electrode, and other specific functional groups. In terms of calculations, the measured potential is then related to the analyte concentration through the Nernst equation, allowing for quantitative analysis. The next one is coulometry. For coulometry, this specific method measures the total amount of charge or expressed in current multiplied by time that passes during an electrolysis process. This is using an applied potential which drives the complete conversion of the analyte at the electrode, thus consuming a specific amount of charge. This is suitable for analytes that are readily oxidized or reduced at controlled potentials, such as metal ions, electroactive organic molecules, and for water, specifically for Carl Fisher water determinations. In terms of calculations, Knowing or being familiar with the Faraday's constant, specifically the charge per mole of electrons, and the measured charge allows for quantitative determination of the analyte concentration. And lastly, we have voltammetry. So voltammetry measures the current response of an electrode as its potential is systematically varied. For its mechanism, this involves a scanning of potential using different analytes in the solution which undergoes oxidation reduction reaction and using their characteristic potential. So this variation of the potentials results in peaks or waves in the current potential curve. So this is highly applicable because it is highly versatile, being applicable to wide range of analytes, including inorganic ions, organic molecules, biomolecules, and even nanoparticles. So for calculations, peak heights, peak areas, and peak potentials in the voltammogram can be used for qualitative and quantitative analysis, providing information on analyte identity, concentration, and redox behavior. With regards to analyte specification, as I've mentioned earlier, potentiometry is usually used for heavy metal detection like chromium, lead, nickel, and copper. This is also prominently used in pH measurements. Meanwhile, coulometry is highly used in electroplating, which are used for electronics, jewelry, and medical implant applications. Coulometry is also used for water purification. Lastly, voltammetry is somehow usable for environmental monitoring and battery testing. The versatility of electrochemical methods lies in their diverse and specific nature. Understanding the principles of each technique and its ideal analytes, as well as the relevant calculations, empowers researchers and us students to delve into the chemical world at the electrode interface. From a simple ion analysis to complex biomolecule interactions, electrochemical methods continue to provide invaluable insights into various fields of science and technology. Before we end this discussion, let us consider this situational sample problem. So imagine you're an environmental chemist who's responsible for monitoring the lead content in a community's drinking water supply. So with this one, you're given 3 tasks and you are expected to choose the appropriate or most applicable electrochemical technique on the specific tasks. So you are given the idea to consider the following factors for each task, which are sensitivity, selectivity, ease of use, and the ability of providing quantitative and qualitative information. So you can recall the characteristics of potentiometry, coulometry, and voltammetry as we have previously discussed. Then choose the best technique based on its strengths and limitations in this specific context. So you may pause the video and share your answers in the comments. This marks the end of the discussion of electrochemical methods part 1. Thank you.